In this video, we're going to introduce the idea of a parametric curve. And depending on your background in algebra, you may have been introduced to these curves before now, but I'm not going to assume any prior knowledge, but I'm just going to give you a quick intro into what a parametric curve is. And then in subsequent videos, I will help you visualize what some of these curves are. And then ultimately, our goal is to be able to do calculus with these curves. Right? So I'm going to write down a few equations here and then just say something about them. So let's say you have an equation y equals f of x. And then let's say you have another equation like x equals h of y. And then let's say you have something like this, an uppercase G of x comma y is equal to c, where let's say c is some real constant. All right. Let me fix my x here. So these obviously are different equations. Just on the surface, they look different, right? But however, they have something important in common in the fact that if you take each of these equations by themselves, and then you graph them, right? Which we love to do with equations. We love to visualize them in the form of a graph. Well, it turns out all of these these are different ways that we can represent equations of curves, right? And these are curves in 2 dimensions. So I'm going to, in kind of a global way, just sort of classify or categorize these equations and say this. This is a one or single equation representation, right, of a curve in 2D. All right, yeah, so again, think about like your y equals x squared, or if you flip it around and you have like x equals y squared, or if you have something like x squared minus y squared equals 10. All those equations, right, they in some way, depending on your technology or even your own individual graphing ability, you can graph those equations and then you'll see a curve. Notice I'm not necessarily saying that it represents a function, right? Some of them might be functions, but at the very least, we can represent curves in 2 dimensions in one of these ways, right? Well, so now let's introduce what's new with this idea about parametric curves. Well, on this side, I'm going to write down 2 equations. I'm going to use our standard variables, x equals, and then y equals. And then let's say that x equals something like f of t. And then y is equal to something like h of t. Right? So notice here on the left-hand side of these equations, I have my standard variables, x and y. I haven't indicated if one is independent and one is dependent. I'm just saying here are my 2 variables. But then I say that each variable is a function of this new letter that I'm introducing, t, right? So x is a function of t, y is a function of t, and together these 2 equations, so let me put a brace there. This is now a 2 equation. In other words, with these 2 equations, I can represent, so it's a 2 equation representation of some curve, so of a curve in 2 dimensions, right? And this new letter that I'm using, t, this t is called, so t is called a parameter. A parameter. It is something that we as the user, or maybe I should say as the definer of this thing, we can control t. So we can pick values of t. Hopefully we choose them wisely. And then when I plug the t value into the top equation, I get the x coordinate of the point. And then when I plug the t value in the second equation here, the h equation, I'll get the y coordinate. And I can still then plot that ordered pair x comma y in 2 dimensions. So all together now, this pair of equations is what we represent, or what we call the parametric equations for this curve, right? So let's write that down. So all of this is the parametric equations, or these are the parametric equations for the curve. All right. And so that's what we're going to be focusing on now, right? So here, just again, to introduce the idea, if you've never seen it before, let's do a quick example where we pick one of these parametric curves, and I show you, okay, what do you do with t? And then how could you eventually plot this? Because I'm claiming that this is another way that you can represent curves. So let's look at this example. And I will say, here are our parametric equations. So let's say x is equal to t squared plus t. And then let's say y is equal to 2t minus 1. All right. Now, if you remember, like when you were first introduced to functions and equations and then graphing these equations, you would then take an equation and then you would just pick a few points, right? You just pick a few points, and then you would figure out what the ordered pairs are at those points, and then you would plot them, and then you try to connect them with a nice smooth curve. Let's try to do the exact same thing here, but now what we're going to be picking is our points are going to depend on what values of t that we are going to pick. So I'm going to say this. I'm just going to start with a table. Let's just make a table. And I am truly, you might not think this is random, but I'm going to randomly choose some values for t. And I'm going to put those values there. And I don't know what it is about the number 5. But typically, you know, when you're plotting curves and they're not linear graphs or anything like that, typically if you get like 5 or 6 points, that tends, and if you choose them wisely, right, then you tend to get a pretty good picture of what the curve is. So here are the 5 values of t I am going to pick. I'm going to pick -2, -1, -1/2. Yes, I'm going to show you that you can pick fractions. 0 is always a nice one to pick, and then I'm going to pick a +1. All right. So these are the values of our parameter. And, you know, depending on the equations that are here, you can pick any values of t that you would want, right? So I'm just picking these values. I'm picking a few negative and then a couple, 0 and then one that's positive. And then the next column, I'm going to figure out what the corresponding x value is. And then the third column will have the corresponding y value. And then we'll have, actually, I'll just do this. I'm going to do a fourth column just with the ordered pairs. And these are the ordered pairs that we will actually plot. You don't actually plot the t, right? The t is just used as a way to generate the x and y. And we're going to plot them in the same sort of ordered pair fashion in our xy plane. All right, so let's get to it. Let's say, let's take our x values. I'm going to say x evaluated at -2. And I'm going to do the evaluation pretty quickly. This is going to be 4 plus -2, so I have a +2, and then I just put this there, right? Let's do x of -1. If I plug -1 in, I will have a +1 after I square it, and then I have to add -1, so that gives me 0. So I'm going to do this. If I plug 1/2 in, I'm sorry, -1/2. -1/2 squared is 1/4, and then plus -1/2. This gives me a -1/4. So I'm going to put that right there. And then obviously when I plug 0 in, I'm not even going to write that one down. I'll get 0. And similarly, when I plug 1 in, I'll get 2. I'm just going to put that in there. There we go. So right away, we have the 5 x values that correspond to these 5 t values. Then we do the same thing to get the y's, right? But we're using the same values of t, but now we're going to use the y equation. So again, I'll just write down a few of these values. Now let's do y of -2. So that's -4 minus 1, that's -5. So I'm going to put a -5 there. With t equals -1, plug that in there, what do we get? We get -2 minus 1, that's -3, so it's right here. And then if we plug -1/2 in, I think we're going to get -2. So let me scroll down a little bit here, give myself some more room. So y of -1/2, it will be -1 minus 1, so that's -2. So it's right there. When I plug 0 in, I get -1. When I plug 1 in, I get a +1. There we go. So here are our ordered pairs that we're going to plot. 2, -5, 0, -3, -1/4, -2, 0, -1, and then 2, 1. All right, nothing difficult about this. So now what is our plot going to look like? Well, we're going to use our standard XY plane. That's nice. And let's see, if we look at our Y values, well, the smallest Y value is -5, so maybe I'll extend this a little bit more. And then the smallest X value is -1/4, so that should be fine. And then the largest, the biggest Y value here is 1. So let's do this. So maybe 1, 2, 1, 2, 3, 4, 5. And then let's go up, let's say this is -1. I'm just going to put the 1 there, and then we can see the scale that I'm using. And then we really don't need to go too far on the x-axis. But this is our typical y-axis. This is the typical x-axis. And now let's plot the ordered pair. So I'm going to plot them so that they kind of stand out. So 2, -5, roughly here. I noticed this was like I'll say we got this ordered pair by plugging in the first value of t. So I'm going to say this is when t is equal to -2. And then when t is equal to -1, we get 0, -3. So 0, -3, that means it's the y-intercept. So it's right here, right? So this was what we got when we plugged -1 in. So I'll do that. And then -1/4 and -2. So -1/4, kind of break this up into fourths. 1, so probably about here. And then -2 is right about here. So this is when we plugged t equals -1/2 in. And then when t is equal to 0, so x is, so it's 0, -1, so that's right here. So this is when t is equal to 0. And then the last point is at 2, 1, so all the way up here. So then this is when t is equal to 1. So when we look at this, yeah, we would have to kind of connect these points. Let's see here. Yeah, so let's see if we can connect them and get a curve. So something that looks maybe like that. Something like that, right? But anyway, yeah, so this would be our curve. When I look at it, it doesn't look like that this curve represents y as a function of x. Remember your wonderful vertical line test? We can see that it doesn't pass the vertical line test. So we can't say that y is a function of x, but it definitely is a curve. And the other thing I'll say too is notice that with this, as we increased t, right? So as we chose bigger and bigger values of t, we started at this point, and then it's like we added a certain direction, and then the curve ended up doing something like this. So the arrow here, these little arrows, they represent the direction of the curve. So this is the direction of the curve. And it's also referred to as the orientation of the curve. And this is something your quote-unquote regular curves don't have. So like your y equals f of x or your x equals h of y, they don't have a natural orientation or a direction, but your parametric curves do. And parametric curves if they now allow you to define a direction, then that means you can do a lot more cool things with it, right? So that's our first example of a parametric curve. And I chose, let me go back up here just a little bit. I chose these equations because the functions are, relatively easy to evaluate. But now basically you could have any of the functions that you're used to here that represents your x, and then similarly any function, right, that you can think about, right? Exponential functions, logarithmic functions, trigonometric functions actually are very important in a parametric way. And I want to end this short video with an example of a pair of parametric equations that you have used quite a bit, right? So here's another example, right? And let's do something like this. Suppose x is equal to the cosine of t, and then your y is equal to the sine of t, and then let's specify what range of values we're going to use for t. So let's say we use something like t going from 0 to 2 pi. If you had to take a guess to think about what this pair of parametric equations would look like if we were to graph it, what do you think you would come up with, right? Think of how you may have been introduced to trigonometric functions, where you were told that the x coordinates on a certain curve represent the cosine value, and the y coordinates on a certain curve represent the sine value. Do you remember what that curve is? Well, that curve is the famous unit circle. So this is the parametric way of defining the unit circle, but it's not complete until you add the range of possible values of your parameter. So yeah, if you were to sketch this, if you were to go through, and I encourage you to try to do it, maybe it's a good refresher as far as your using values on the unit circle are concerned, what you would get is, in fact, I'm going to mark off the important points here. Basically the x and y coordinates. So you'd have -1 there, -1 there. So when you start with t equals 0, you would have a cosine value of 1, which means your x is 1, but a sine value of 0. The sine of 0 is 0, the cosine of 0 is 1. So you would start here. And then let's go over here. Now going due north, right, in 90 degrees, in radians, that will be pi over 2. The cosine of pi over 2 is 0. The sine of pi over 2 is 1. So you're now right here. And then going in this direction, due west is pi. In fact, let me go ahead and write these here. So this is when t is equal to 0. That's that ray. This is the ray t equals pi over 2. This is the ray t equals pi. And then down here, this is the ray, you might remember, 3 pi over 2. And it turns out, just using these 4 values, you'll get the ordered pairs that I'm highlighting right here. And then if you were to use other special values like pi over 4 and pi over 3, pi over 6, you would get a few more ordered pairs. But what you would end up is this, and I'm going to sketch the curve in with this specific direction now. When t is equal to 0, you would start here, and then it's like you would go counterclockwise like this until you get back to when t equals 2 pi, so you're like that, right? And this is your famous unit circle, right? And you might remember, again, this sort of definition of sine or cosine. And then the other thing I would do, this is the last thing I'm going to do, is to say, let's take this equation and let's modify, let's do a couple of things with it. I'm going to square both sides of both equations. So I'm going to do that. And then I'm going to do that. Right? And then for fun, right, because addition is so much fun, I'm going to add both sides here. So when I add the left-hand side, I will get x squared plus y squared. And then when I add the right-hand sides, I will have cosine squared of t plus sine squared of t. And boy, have we seen and used this identity several times, even just, not too long ago. But cosine squared plus sine squared is always equal to 1. And there you go. We've now taken the parametric equations, we've done a little bit of math magic on it, and now we've come up with this equation for the unit circle that you might remember, right? So this is now the implicit form, right? So let me just highlight this. So again, this is the parametric form of our unit circle, and then now this is the implicit form of our unit circle. And if we wanted to, we could try to get it explicit by solving for y, but that's going to lead to a couple other important concepts that will take us a little bit away from where we need to be. So I think this is sort of a good intro. I know it was a very quick intro, and if you've never seen parametric curves before, you can, I would say, watch the video again, and you can look for other videos out there as well that might give you a few more examples. And we are going to see more examples of the parametric curves. It's just that our focus will be on how do you do calculus with these curves. Like, what if you wanted to find the slope of this curve here, and all you have is the parametric equations? What can you do to find the slope of a curve? And we're also going to talk about area, again, as it relates to these parametric curves. So I hope you found this little intro interesting, and I look forward to seeing you in another video.